In the vast universe, where mysteries abound and the very fabric of space-time is stretched to its limits, a profound mystery has emerged. Our understanding of the expansion of the universe is at a crossroads, with new evidence challenging long-standing theories and hinting at hidden forces that could reshape the very foundations of cosmology. Join us on a journey through the latest discoveries and deep dives into the secrets of the universe as we explore the fascinating and controversial question: how fast is the universe really expanding? Something is wrong with our understanding of the universe. Cosmology seems to be heading toward a confrontation over one of its most fundamental questions: how fast is the universe expanding? For more than a decade, the two sets of measures have been in conflict. Observations of the universe today generally show that the rate of expansion, known as the Hubble constant, is about 9% faster than predictions based on data from the early universe. Researchers hope the James Webb Space Telescope, the most advanced telescope ever built, would help settle the question once and for all. But so far, no consensus has been reached. Instead, the Space Observatory has reinforced the discrepancy with astonishingly precise new observations that threaten to overturn the standard model of cosmology. The new physics needed to revise or even replace this 40-year-old theory is currently the subject of debate. One interesting and intriguing possibility is that there is something we don't understand about the universe. Join us as we explore the new superdeep images from James Webb that have just confirmed that there is something seriously wrong with our understanding of the universe. Our universe began with an explosion, the Big Bang. Energy, mass, and space came into existence in a fleeting moment. Then the young universe formed, a bubbling, expanding plasma of matter and antimatter particles that seemed to annihilate only on contact. Left to their own devices, the matter and antimatter within this plasma should have consumed each other, but scientists believe that an unknown imbalance allowed more matter than antimatter to be created, thus saving the plasma universe from instant self-destruction. Gravity squeezed the pockets of plasma, compressing and heating the material so that sound waves traveling at half the speed of light, called baryonic acoustic oscillations, rippled across their surfaces. Meanwhile, the high energy density of the early universe and its jumbled contents stretched space-time, pulling a small portion of that matter out of the fray as the universe inflated like a balloon. The standard story goes that ordinary matter, interacting with light, coalesced around invisible clumps of dark matter to form the first galaxies, linked together by a vast cosmic web. Initially, as the contents of the universe expanded, its energy density and therefore its rate of expansion decreased. But then, about 5 billion years ago, the galaxies began to move backwards at an ever-increasing rate. The cause was another invisible and mysterious entity called dark energy. The simplest and most popular explanation of dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at all times, woven into the elastic fabric of space-time. Einstein named it lambda in his general theory of relativity. As our universe has expanded, its overall matter density has decreased while the dark energy density has remained the same, gradually making dark matter the largest contributor to its overall expansion. Taken together, the energy densities of ordinary matter, dark energy, and light energy set an upper limit on the rate of expansion of the universe. They are also key ingredients in the cosmological lambda cold dark matter model, lambda CDM, which maps the evolution of the universe and predicts its end, with matter eventually spreading so thin that it will undergo a heat death known as the Great Freeze. Many of the model's predictions have proven remarkably accurate. However, this is where the problems begin. Despite much research, astronomers still don't know what dark matter or dark energy is. As Ofer Lahav, professor of astronomy at University College London who studies dark energy in galaxies, puts it, most people agree that the current composition of the universe is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is that we don't understand the last two. But an even bigger threat to the lambda CDM model has emerged. Depending on the method astrophysicists use, the universe appears to be growing at different rates, a difference known as the Hubble tension. Tests of the early universe show that it was expanding much faster than lambda CDM predicted. These methods have been verified and confirmed by countless observations. So, as astrophysicist Adam Rees, Nobel laureate and leader of the team that made James Webb's new measurement, said, "The only reason I can understand at this point why they disagree the idea is that the model we have between them might be missing something. Measuring the expansion of the universe requires a little more than radar." The first method to measure this growth looked at the so-called cosmic microwave background, CMB, a remnant of the first light in the universe created just 380,000 years after the Big Bang. This trace is visible all over the sky, and it was mapped by the European Space Agency's Planck satellite to find the Hubble constant with an error of less than 1% from 2009 to 2013. In the image M, this baby universe, the universe is almost completely homogeneous, but the hotter and colder regions where matter is more or less dense reveal places where the baryon's acoustic vibrations have caused it to clump together. As the universe exploded outward, this soap bubble structure transformed into a cosmic web, a network of crisscrossing filaments along the intersections of galaxies that would have been born. By studying these ripples with the Planck satellite, cosmologists have deduced the amounts of normal and dark matter, as well as the value of the cosmological constant, or dark energy. Integrating them into the standard model gives a Hubble constant of about 67 kilometers per second per megaparsec. Let's focus on that number for a moment. If a galaxy is 1 megaparsec away from us, that means it is moving away from us, and we from it, at a speed of 67 kilometers per second. At 20 megaparsecs, this rate of collapse reaches 1,340 kilometers per second and continues to increase exponentially from there. If a galaxy is more than 4,175 megaparsecs away, it is moving away from us faster than the speed of light. A second method of finding this expansion rate uses pulsating stars called Cepheid variables, dying stars whose outer layers of helium grow and shrink as they absorb and release stars and radiation, causing them to periodically blink like distant beacons. In 1912, astronomer Henrietta Swan-Leavitt discovered that the brighter a Cepheid star, the slower it blinks, allowing astronomers to measure a star's absolute brightness and thus estimate its distance. It was a historic discovery that made Cepheids the ubiquitous standard candles for measuring the vast scale of the universe. By stringing together observations of moving Cepheid stars, astronomers can construct scales of cosmic distances, with each step taking them back in time. It is one of the most accurate ways astronomers today use to measure distances. To construct a distance ladder, astronomers first construct the ladder by selecting nearby Cepheids and checking their distances against light pulsing with light found geometrically. Wendy Friedman, an astrophysicist at the University of Chicago, said the next steps were added using only the Cepheid figures. Next, astronomers looked at the distances of the stars and supernovae on each bar and compared the magnitude of the red shift of their light, which stretches toward longer, red wavelengths. Then when the universe expanded, this allowed for a precise measurement of the Hubble constant. In 2019, Rees and colleagues used this method to aim the Hubble Space Telescope at one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their results were explosive, an incredibly high expansion rate, 74 kilometers per second per megaparsec, compared to Planck's measurement. However, Hubble lacked the precision needed for the messy regions of space the team was studying, causing some of the distant Cepheids to blend in with nearby stars. Dissident cosmologists have had some time to argue that this shocking result could have come from a measurement error. So when James Webb launched in December 2021, it was ready to either resolve this discrepancy or merge it. At 6.5 meters wide, Webb's mirror is nearly 3 times larger than Hubble's, which is just 2.4 meters wide. Not only can James Webb detect objects 100 times fainter than Hubble, it's also much more sensitive in the infrared spectrum, allowing it to see across a wider range of wavelengths. By comparing the Cepheids measured by James Webb in the galaxy NGC 4258 with bright-type I supernovae, another type of standard candle, because they all erupt at the same absolute brightness, in distant galaxies, Rees and his colleagues came up with a nearly identical result, 73 kilometers per hour, second per megaparsec. Other measurements, including one made by Friedman with the Hubble Space Telescope of the rapid brightening of the brighter part of the red giant branch and another of light bent by gravity from large galaxies, returned results of 69.6 and 66.6 kilometers per megaparsec, respectively. Another result using light bending also gave a value of 73 kilometers per second per megaparsec. Cosmologists were puzzled. According to Rongan Kai, a cosmologist at the University of California, Merced, who worked on the Hubble voltage interpretation, the temperature of the CMB is measured to 1% accuracy and the distance scale of the Cepheids.